Okay, so I'm going to be working through number 4. So there's a lot of ways to think about number 4. Here we have a metal bar that's suspended by 2 ropes with T1 and T2 in the rope. And then there's 3 masses hanging from the bar, and we're trying to figure out the tensions in the 2 wires. Okay. Well, the first thing that we know for sure is that T1 plus T2 has to equal the total mass of the system, or everything hanging, including the bar, times G, right? Because they're hanging. It's not accelerating up or down. So we know this for sure. And the mass of the entire system, if you add it all up, the bar is 25, then 25. So 25 plus 5 plus 15 plus 10, that's 55, unless I'm crazy. And I'm not that crazy. So this turns into 55 times 9.8, which means that, again, I'm not breaking any new ground here. It is 539 newtons. Okay, so whatever the tension is in one, if we can figure out the tension in either T1 or T2, then we're able to figure out the tension in the other because the total tension has to be 539. Now, the tension is not going to be distributed equally because if you look at the masses are not distributed equally. All right, so how do we figure out this other idea, right? Because if you have one equation, 2 unknowns, you can't solve it. There's got to be something else that we should be able to figure out with physics, like some other relationship. And once we discover that relationship, we can solve. All right, so I'm going to show how to do this several different ways. The first way to think about this problem is to pick a point and figure out all the torques acting on that point. So let's just pretend, for argument's sake, that your point is right there, all right? That would mean that the 5 kilogram box does not exert a torque because it goes through the axis of rotation. However, there is a torque up here, there is a torque down here, there is a torque up here, there's a torque down here, and then the center, remember this bar weighs something. So the center of mass, this is a uniform bar, it's going to be in the middle of the bar, and so we'll just put it right there. And so that torque is going to go this way. The one thing, again, we know that about all these torques is that they are the net torque is 0. So if you think about this, the torque, not T1 plus T2, but the torque on at point let me rephrase that. The torque supplied by T1 and T2 have to completely equal the torque downward from the center of mass plus the 15 plus the 10 kilogram objects. So that's one way to think about it. So if you think about it logically, you would have an equation where you would have T1 times 2 plus T2 times, what is that, 5? This is 5. Equals 25 times 9.8 times 3. You could set it up that way. Okay, I'm not going to solve it like that. So that's one way you could solve this thing. There is another way you could solve it, and I'll do this one in green. Let's say that we do something else. We could actually pick this point. We could pick a point, but that might seem like a more natural pivot point, just because if you think about it, if you cut T2, this would act as the pivot point, T1. So now let's just think of what are all the torques about this point. Well, there's a torque downward here. The center of mass provides a torque downward here. This provides a torque downward here. T2 provides a torque upward, and this one provides a torque downward. And what do we know about this? In this case, we got to figure out just because I'm talking about this one right now. This torque and this torque are working together because they are both trying to produce a counterclockwise rotation. So it is super important that you not lump in this torque along with these objects here because they are not going in the same direction in terms of torque. So you could do it this way if one were so inclined. Oopsies. And in this case, you would have the torque here and the torque here added together, and then you subtract off the other 3 torques, and that equals 0. Okay, that's another way to do it. There is yet another way to do this, although I'm not going to get too in-depth, which is you could pick this as the pivot point, and then boom, you got boom, 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 in which case this torque and this torque act together. The last way you could do it is, whatever. Pick this as your pivot, and then we got boom. This, remember, this does not produce anything. Boom, 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 this way. All right. Now that I've shown you the several different ways, and I haven't even exhausted all the ways to think about this problem, but that's probably the easiest 4 ways you can think about this problem. All right. So what I'm going to do is I'm just going to pick this one. All right. So we're going to have this torque at about the center of mass, torque, torque, torque. So we're going to have T1, and this is at a distance of 2, plus T2 at a distance of 5 equals. Now here we're gonna, remember this 5 does not produce a torque if I'm picking this as the axis of rotation, so we're gonna skip that one. We'll start with the center of mass. So it'll be 25 times 9.8. Since this is a uniform bar, a distance of 6 across, that means that this right here has got to be 1, which means it is a distance of 3. Well, it makes sense, it's the middle of the bar, right? That 15 looks like it's a distance of 4 away. And then this last one, the 10, is a full distance of 6 away. All right. So I'm not going to go through the algebra on this, but I will note that now you should be able to substitute out one of the T1s and the T2s. Let me pull out my... Well, I just erased my answer, but let me just pull out what I had written. That when you do solve this, T1 is approximately, again, depending on your rounding, I'm going to say 278 newtons, and T2 is approximately 261 newtons, and there might be some, some change in there, but this is definitely within a couple tenths of a newton. So that is how you would solve it. Just a interesting side note that if you were to solve it using one of, again, this is just an interesting side note, that if you were to solve it this way, using one of the the tension, one of the ropes as the pivot point, you would not have both expressions. You would not have T1 and T2 in your formula because this one would not be present, right? It just wouldn't exist, so I X it out. In which case, you would only have, and this wouldn't be the formula, but you would only have an expression with a T2 in there, and you could just, some might call that an easier calculation, but then you would just substitute in there, and then just, the reason it would be slightly simpler is that you wouldn't have to do the substitution because you would have T2 equaling some number, and you could just instantly solve or quickly solve for T2 without having to do a substitution. But doing it the way I showed is just one more step. It's a substitution, but hey, you know what? You kind of pick your poison. If you pick an axis of rotation on one of the ends, you're gonna have a real quick substitution of either T1 or T2. If you happen to pick one of the pivot points to be at the rope, then you're not going to have that substitution. You're just going to be able to immediately solve for what T1 or T2 is, and then just do a subtraction.